So, dear colleagues, I'd like to introduce you to Reinis Baranovskis, who is a PhD student at the University of Latvia, who will be talking about the diamagnetic levitation today. And so, please, Reinis, you can start.
Thank you for the introduction. I'm Reinis Baranovskis from University of Latvia, and I'll talk about topics of induction heating as well and levitation of molten metals. So, I'm a PhD student in University of Latvia, which is the nation's largest university of 15,000 students. And I work in Institute of Physics, which encompasses 50 scientists which work on magnetohydrodynamics. We are one of the leading centers in the world doing this research. And that means we do fundamental and applied studies involving complex interactions of electromagnetic fields and liquid metals, which in one word we call magnetohydrodynamics. It froze a bit. I'll try to get to the next slide. So, in the whole big world of physics, magnetohydrodynamics is a very specific niche. If we take in the world, there are about 1 million physicists, active ones. And then when we go all the way to the subfields of continuum mechanics, fluid mechanics, we find magnetohydrodynamics that deal with conductive fluids. But most of the research there is about plasma physics, and we are in the smallest subfield, which we call resistive MHD, which deals with liquid metals and semiconductors and how these electromagnetic fields interact with this conductive media. Magnetohydrodynamics is governed by Maxwell's laws of electromagnetism and fluid mechanics equations. So we have two very often used tools in our experimental work, which are the permanent magnets and electromagnetic coils. With both of them, we can create a static magnetic field and also alternating magnetic field. And for us, the most interesting one is alternating magnetic field, which gives us opportunity to do work and induce currents in any conductive media, which would be metal, but not limited to that. And there are two main effects which we can exploit and how we can interact with these with the metals. First one, we create a force distribution in the whole conductive media. And the second one, we create a power density or dissipated power, which in simplified terms is heating. With these two effects, we have a multitude of applications. We are researching in our laboratory. The most straightforward are liquid metal steering and transport. I've worked there extensively as well, making machines that steers or transports in laboratory gallium alloys, but in industrial scale that would be light alloys as aluminum. We interact with the liquid metals when they crystallize. By doing that, we can change the properties when they crystallize, and that determines the mechanical properties and so on. And we, of course, strive to improve those properties by affecting these crystallization conditions. Also, we've explored surface deformations of these liquid metals, and one of the applications have been inducing surface waves to increase the liquid metal surface area to improve silicon refining process. And we worked on both numerical and experimental models validating this method. We also research energy topic, and there liquid metals arise in one specific and interesting application of liquid metal batteries. We looked specifically not to the energy storage part, but over the stability part. Since there, in this proposed setup, we have multiple layers of conducting fluids. And these conducting fluids are passed current through, and that creates instabilities. And the last application we do, I personally do, and which is my PhD thesis, is aluminum degassing. There again, the aim is to improve one of the metallurgical steps, which is hydrogen removal from aluminum. And I work in a laboratory with experimental models which test fluid dynamics of a permanent magnet system, of a liquid metal system, which has a flow field inside of it, created pressures. And I try to measure this flow field and scale and predict what kind of fluid dynamics it would have in a real large-scale systems, where we would try to contactlessly interact with this aluminum. But now getting closer to the topic of today's speech, we need some kind of electromagnetic field. To do work, this electromagnetic field has to be alternating. So let's introduce mathematically alternating magnetic field by having some kind of amplitude of B0 at each point of the space, and it changes harmonically in time. And this change harmonically in time is represented by this sinus omega t function. On the right, you can see an animation where we're just a workpiece inductor, and how it in one period the magnetic field would change. Here is animation of the magnetic field distribution in a conductor. It's an aluminum conductor put in an electromagnetic coil with the color magnetic field strength intensity is represented. And what changes in this video was the frequency, and when frequency changes, the field distribution also changes. We can look at the same effect for the current density. When we change the frequency, the current distribution drastically changes. And here we worked only with frequency range of 1 to 10,000 hertz. And this leads us to the first physics principle I'm going to explain today about a skin effect. So in such a workpiece, when we have put a conducting material in an inductor which has changing magnetic field, inside of this metal or in this workpiece, the total magnetic field is sum of two fields. One is the external field produced by electromagnetic coil, and another component is induced magnetic field, which happens because of Maxwell's Faraday law of induction. So what happens when we change the frequency? The applied magnetic field amplitude of it does not change. However, for the induced magnetic field, I've taken a derivative, because that's what happens if you take a Maxwell's equations. You have to take time derivative of this magnetic field. We see that this induced part is proportional to the frequency. So thus changing the frequency changes the ratio of external magnetic field and induced magnetic field, and that causes skin effect, which tells us how the field distribution happens. And here I have written an analytical, this is a precise analytical solution for 1D case. It's a quite a long formula, but for our purposes, we shall ignore the large part in the brackets, and we can look at only this part where magnetic field in a distance of x inside of the conductor falls off exponentially from the surface. And the constant which dictates how quickly this field decays, this constant in the exponent, is called skin depth. As you can see, it depends on firstly on the frequency, and secondly on material properties we are having. So when we raise the frequency, when we have a good electrical conductor which has a really good electrical conductivity, and when we have magnetic properties, and the depth of which this alternating field can penetrate the conductor is reduced. And also that's why this is both applicable to transmission lines. This is applicable to electromagnetic shielding. But for our case, since our conductors are really large, the cross sections of it, it's also will be applicable in our cases of electromagnetic material processing. And this is how with the magnetic field would decay in a cylindrical workpiece. I have driven a line where I represent it. And when we increase the frequency, the magnetic field is expulsed out of pushed out of the conductor. The same happens for, as I said, for magnetic field and for electric field. The situations, they're really connected. And by definition, within one skin depth, which is has dimensions of just distance units of meters, the intensity by definition falls to about 37% of the original applied electric or magnetic field or alternative current. But when we talk about power distribution, power is proportional to the current squared in induction heating. The decay happens even more drastically since we square this term of current, and thus we have twice as fast decay of power density when we look at our workpiece, and 86% of power is already dissipated in the first depth of one delta. So why alternating field heats conductors? Super simple explanation would be saying that changing electromagnetic field flux causes EMF, and that causes currents in our conductor in our circuit with resistance R. A bit more sophisticated explanations would be look at Maxwell's law and Maxwell's Faraday law of induction. Its root of electric field equals to time derivative of magnetic field with a minus sign. The minus sign is important there. So from there we can replace the electric field with current density, which is electric field in a conductor with the said electrical properties. And from there we can really connect that changing magnetic field creates current distribution. There is a rotor here which makes it quite difficult to predict simply on how would it look like, but definitely if in the left hand and right hand has to be balanced. If this part is non-zero, and when the magnetic field is changing, there has to be electrical currents passing through. And thus we come to induction heating, and at this process of heating electrically conductive materials with alternate magnetic fields. These usually a coil called an inductor creates this alternating magnetic field, which induces eddy currents in the workpiece, and that causes Joule heating. This method mostly is used in metals, but also it can be used in semiconductors when sufficiently high temperatures are reached. There exists empirically found optimal values how you have to adjust your frequency. It isn't the case that higher the frequency, the better the heating. Since we have this parasitic effect of skin effect, there is an optimum ratio to skin depth and our workpiece diameter. On the right side, I'm showing you how our coil heats steel. And here again, you can see the different diameter workpieces here have different temperatures, and they all have reached their equilibrium state here. And the engineers have empirically found that this ratio of diameter and skin depth should be around 3 to 4, and then maximum power densities can be achieved. And I'm here showing you one of our experiments I did where we heated steel discs The frequency we use here is around 17,000 hertz or 17 kilohertz. Currents is in a couple of hundreds. Magnetic field is 30 to 40 milliteslas. And with such currents, you obviously need water cooling. Otherwise, your coil would overheat, and all of the inductors are usually water cooled. That's an experimental property. And skin depth to these material properties would be 3 millimeters around. And judging by temperatures, we can heat steel about 1000 degrees. Here, all the heating took place within a couple of minutes, but there exists applications where you can heat, especially steel, to red glowing hot within a couple of seconds. I've seen demonstrations from German industry where you really increase the current in the coil, and you can achieve tremendously quick heating and that's used in induction hardening, for example, where you have a workpiece and you want to heat the outer layer of your workpiece. Let's say it's a crankshaft, and thus you can heat only the outer part of the crankshaft to change steel properties. It undergoes a phase change, and in the center, temperature has not changed. It's moving on. There's another demonstration where we put in aluminum, and within a minute, aluminum is lower melting temperature of 660 degrees. One can melt aluminum. And yeah, here is the demonstration. It's under the glass, so it doesn't spill out. But again, within a minute, aluminum is melted. So overall, wrapping up the induction heating, the benefits to one thing I would like you to remember, that the induction heating is a direct heating method. So the heat is generated in the workpiece, and that allows us for some very high power densities, more than maybe other methods. Let's say if we compare it to the gas heating heats only the surface. But when you can heat the workpiece itself, you can achieve tremendously high temperatures. There exists applications where you heat metals up to 2000 degrees and oxides up to 3000 degrees, for example, zirconium oxides. And at those temperatures, you can get electrical conductivity in the glass and metal oxides, and the world is completely different. And at those temperatures, you don't even have a crucible where to put all these materials. You're really limited to your, sometimes have to do semi-levitation, where the material doesn't touch the walls of your crucible where you're trying to melt it. Of course, there are like other advantages, like since it's an electrical method, there's a high degree of control. It's a contactless method, you don't have to touch it. And there's little or no pollution, and it's quite safe to operate. Sometimes you have these massive currents and only just a couple of volts applied to the inductor. Of course, there are some also drawbacks. This method can be applied only when you have an electrical conductor. Often you need like complex power supplies to operate it, especially when you need to get to larger size and to odd frequencies, which are not found in everyday applications. And precise predictions requires 3D modeling of electromagnetic and a heat transfer problem. So I'm showing you the same aluminum experiment, but without the glass lid on. So by simply putting this aluminum in the inductor and pressing on button, we can see there are forces there. Even if we haven't altered the coil or haven't made any special coil, this demonstrates that there exist also forces exerted on the metal. And we did have a research project, where we tried to exploit this effect, that we can use combination of alternating magnetic field and DC magnetic field, which I call a static magnetic field. And what did we do? So on the right, you have a sketch of the experiment. I'll show later how the top view, how this metal droplets are affected. The blue one is in water-cooled high-frequency inductor, and it's all put in a vacuum, and this red droplet is molten metal. In the videos, you'll see that's copper. And if we put it in the inductor, we can cause forces. When we apply DC magnetic field, we can even cause some larger pressure oscillations. And this is the first I'm trying to get it played. This is okay. This is an instant snapshot from the top, and maybe I'll have a better luck next time. I think I'll launch it manually because otherwise I don't have what to talk about. Okay, here I can launch it manually. So on the left side, this is what happens when we put this copper droplet into alternating magnetic field. There's no static magnetic field. There's only interactions of this medium with alternating magnetic field of 18 kilohertz and almost 85 milliteslas. The droplet is oscillating chaotically. There's other small drops flying around. And when we apply one component of magnetic field, external one, this is created by a permanent magnet assembly, it creates a static field. And in this case, if we go back to our setup, we apply this magnetic field in axial direction, meaning like this magnetic field, only that component. And it's important that we apply only selected components. And that damps movement, reduces the degree of freedom. We have oscillations only in some parts, only on some parts. Only selected components are oscillating. It's not super playing again. I'll try to launch it. Okay. Able to get to the player. In this case, when we reduced the degrees of freedom of movement, we can somehow, with DC magnetic field, we can do the dampening. And this is the result when you dampen the axial component of movement. We get different kind of wobbling. And this is another demonstration. When the droplet is stuck to the wall, there's no movement, and it takes really little forces, and these forces can act only when this droplet is severely levitating. And then finally some kind of perceived rotation happens, and some periodic structure is made here. We'll try to compare three cases side by side. On the left, we have no external magnetic field, only the one that is produced by the coil. On the middle, we have axial field, and here we have transverse field doing the dampening. Temperature estimate, this system is pretty hot. There is a copper and copper oxide here on the melt. And so I'll also show the slow motion of this, how it happens. Here, the most interesting part is regarding the movement of this axial case. Here you can see that there is some kind of wave rotating around, but if we check the particles on the melt, there's very little mass transfer. These particles even are going the opposite direction. So here you have to be careful with these observations, what kind of results we're trying to imply here. And So why did we do these experiments? They look really nice. They look interesting, and the fluid dynamics in such case. But the whole application was to create large enough pressure oscillations to cause cavitation. And why would we want that? This project, the practical aim of this project was to create metal nanocomposites, meaning there is some kind of base metal, and there is and then there is a matrix metal, which are usually metal nanoparticles. And by making such composite, you can improve some of the mechanical properties. But making this composite is not as simple as just adding the particles to the metal, because these nanoparticles stick together, they agglomerate, and they lose the properties, and these properties only can be the improved mechanical properties only can be achieved when the matrix metal is homogeneously dispersed in the melt. And to achieve some kind of dispersion, a cavitation was created. Cavitation is a collapse and creation and collapse of the gas bubbles. You have to have sufficiently high pressure oscillations to cause this cavitation, and it creates some really strong jets in the metal. And with these jets, we try to disperse these agglomerates. Okay, I'll take a drink, and now we'll get to the levitation part. So here I'll show you a demonstration where a magnesium sphere is put in a levitation coil. Magnesium is pretty light alloy and a decent electrical conductor, so it's good for this demonstration. And there are multiple results you can infer from this video. First of all, this is how a levitation coil looks. You have to have a funnel shape, but also some weird. You have another loop of your coil on top of it. You'll see later why. Another interesting thing is that objects you put in the levitation coil starts to spin up, and that's actually a bit of a problem. The spinning can cause destabilization, and there are multiple science papers and scientists trying to figure out the mechanisms of spinning. They've isolated multiple of them, and also how to damp it, how to reduce it in some cases. And here in the video, you could see a block of permanent magnet added to the electrical conductor, and that damped the movement of spinning of it. Okay. So let's talk about the magnetic field, which we need to ensure to make a levitation coil. This was from our practical experiment. There's a coil. At the bottom, the current is going in the one direction, and with the top loop, you have to have it at the opposite direction. And this creates something that's really similar to quadrupole field, although we have more current loops down under, so that makes the field stronger on the bottom side. And here I'm showing you a numerical model, which I created in a software on console multiphysics. It has three coils on the bottom and 2 coils on the top. And with the arrows indicate the magnetic field, and yes, as I said before, these currents on the top and at the bottom, they have to have opposite directions to create such field configuration. The software that calculates it, it takes as a basis, it takes alternating current as a driving force. So it solves the Maxwell's equations in a harmonic form. And let's try to describe what kind of magnetic field we would want to levitate something. The first obvious conclusion, we have to oppose the gravitational forces. In this case, we have a Lorentz force, which is the electromagnetic force, which can oppose the gravitational force. But however, we would like it to be bigger than our gravitational force. However, this condition is not met everywhere. It's really difficult. It's impossible even from theory standpoint to have a magnetic field that has which creates upward force in all of the points of space. And in the video demonstration, you could see how the metal escaped the levitation coil just as it was melting. And this was one of the biggest difficulties in our lab experiments to ensure the metal is not leaking out. And the only thing that's holding it together is surface tension. And so the shape of the droplet we have is determined by the minimum total energy. Similarly, as with surface tension, a droplet takes a spherical shape. And this happens because it wants to minimize the energy, and the spherical shape has the minimum surface area relative to its volume, which is fixed. By same analogy, we can use here and write the total energy. And the difference between the droplet case is that we have multiple terms here. We have the surface tension, which tries to make a sphere out of it. We have a gravitational force tries to flatten the sphere. And in the end, we have magnetic forces. These are expressed with magnetic pressure. This is called the magnetic pressure, and this is magnetic pressure integral. And so what this term will do, essentially, if system wants to minimize its energy, the droplet will want to go with a place where there's the lowest magnetic field. On this case, magnetic field squared. And on this graph, I've plotted this magnetic pressure of this electromagnetic coil. And here you can see it really creates an area in the middle which has the lowest field compared to the surroundings. So everything, if you have a material point there, it will try to go to the center. And essentially, what this means that metal will be repulsed by the inductors or of the current carrying inductor. And that if we cranked up the inductor currents really high, this is the shape which would droplet take, since it would dominate the surface tension forces and the gravitational forces. And now I'm demonstrating you this case, and we're looking at the induced currents only in the spherical object we're levitating. And when we change the frequency, we span here from a couple of hertz to multiple 10,000s of hertz, you can really see the current distribution drastically changes. And with high frequencies, it's completely expulsed out of the conductor. And this becomes important since when something is trying to leak out, you have to understand that the size of the forces on the area where the electromagnetic forces are acting is determined by this skin depth and the skin effect. And if the droplet is invisible to electromagnetic field, it will just leak out. Next up, we can move on to electrical energy. This is basically would explain the heating effect. And as I said previously, it's even more concentrated outside of the electrical conductor, since it's essentially current squared, and most of the heating happens happens underneath the lower part of this spherical object we are theoretically trying to levitate. We can do some order of magnitude estimates of how large objects we could levitate theoretically. If we take a solid object and try to balance the forces, gravity forces and electromagnetic forces, we do that, and this is just an order. This is nothing precise. It's an order of magnitude estimate. We can try to express the linear size of our maximum droplet, and it's proportional to material properties and magnetic field. And if you take characteristic magnetic field we had before, let's say here, okay, I don't have the magnetic field plotted itself, but it's 0.1 millitesla. If we look at 0.1 millitesla, it says that the theoretical maximum size would be around tens of centimeters. If we increase the field to 0.15 milliteslas, we should be able to levitate an object which is half a meter of size. Practically, when we levitate liquids, the electromagnetic forces are not the limitation to this method. The limitation lies in the stability and in the center. As I shown you, that locally there are places where there's no force supporting the droplet. So I used this slide to highlight that raw electromagnetic forces isn't the problem, but the local places where there's zero is the problem. And here I'm showing you a demonstration of the experiment where we levitated molten aluminum. First, it heats up as well. And when it heats up, it even drops in the levitation coil since the electrical conductivity has dropped as a function of temperature. And it looks, filming this was quite interesting. It looks like I've added this in CGI and post-processing. The camera, it's really difficult to capture accurately this effect. I'll try to put it to video again. Okay, never mind. So we also did try levitation of an element called sodium. And why is it so interesting? Sodium is an excellent electrical conductor and very light. Meaning it's really easy to levitate, though there's one problem, but it's chemically super aggressive. If it touches water, it explodes and it burns in the air. So to solve that problem, we just kept it in the oil. And even in air, it had, because of surface forces, it had a layer of oil around it, even when it's melted. And why did we do it? Like, what's the point of this? First, we highlighted really the lightness and the really good electrical conductiveness of the material, since sodium is used in largest magnetohydrodynamic experiments. These are dynamo experiments that try to model movement of flows in Earth's core, and thus predicting and experimentally proving how electromagnetic field of Earth is actually formed. We in University of Latvia had this rigid dynamo experiment, which uses 2 cubic meters of sodium, which is pumped in a helical trajectory path, and thus that creates conditions which can amplify magnetic field, and that's a whole that's the basis of dynamo theory, how the Earth only with the movement of conductor liquid can create magnetic field. And also for the same reason, that's really good electrical conductor. It's light. It can be used as a heat exchanger in a nuclear cooling applications, and that's also large part of where our knowledge and MHD applications are happening. It's in a nuclear industry. My colleagues from University of Latvia also have dealt with modeling these levitation problems, and modeling this, you have to both solve electromagnetic equations, that meaning Maxwell equations, and also solve Navier-Stokes equations for fluid mechanics. And they have created from open source software, referenced AOF software created by Reinis Baranovskis, which can solve such axisymmetrical problem where the droplet is levitating, and this is also compared to experiments. And the same is also done in a bit larger scale. A colleague who now works in the German industry, Sergei Spitans, in his PhD thesis worked on system how to levitate larger amount of aluminum. And he created the system where multiple coils create this magnetic field. And why two coils are better? Essentially, as you can see, the shape is completely different. Instead of one minimum point, you have now 4 points. And essentially, the result of this, his work, was that he could achieve stable levitation for it for larger volumes. And that had applications in really pure metal levitation and manufacturing, one of them being titanium. And here I represented the snapshots of the video here, like this is how the forces look, and which try to support it. And more interestingly for me, that even though the droplet itself is seems to be quite static, on only some waves are on the surface, inside of it there is quite interesting flow patterns. In this case, two large eddies here, and the magnitude is almost 0.5 meter per second. So when you're looking at the experiment, instant of experiment, actually inside of it, there are quite intense flows there. And this is also the results. I wanted to tell a funny story about, he started with an aluminum block, which is heat melted and levitated there. He wrote the mass of it. And even during the experiment and after the experiment, the writing remained on this metal, even though it was in a temperature probably around 800 degrees. And this shows that even though, despite having large and intensive flows inside, on the surface there is a no slip condition where the oxide layer is perfectly still in the place. And we're moving towards the end of my talk. I wanted to mention levitation with static magnetic field to highlight the differences between the cases I've talked about during my presentation. And to levitate something with a static magnetic field, that's a completely different mechanism of levitation. First of all, you don't care about electrical properties, you're interested in diamagnetic properties, meaning you're interested in how well the material is repulsing externally applied magnetic field. And for example, water is diamagnetic. However, to levitate something made out of water, some scientists did the levitation of a frog, you need magnetic and magnetic field gradient multiplication of this to be around so large, more than 1,000 Tesla square to the meter. So you have to have tens of Teslas strong magnetic field to levitate something made out of water. And that requires usually supermagnets when you read the research. And this example on the right, that's a levitation of graphite. It's a paralletical graphite, and one of the most diamagnetic materials if you look at the property table in Wikipedia. And you can have levitation maybe a millimeter above a permanent magnet and a stable one. So I wanted to highlight this so that this is probably what you'll want to do in your experiments. I assume if you're making diamagnetic materials with odd mu, and that's the whole difference, that both magnetic fields, strength, and also the shape of it. Here, the magnetic field gradient is important, and since it's a completely different phenomena. All right, thank you for attending my presentation. If you haven't heard, I do run a successful YouTube channel where I do my science communication. And if you type in YouTube MHD Technology Laboratory, you can subscribe and see my videos on different topics we do, well, different interesting topics we do in our research. Thank you very much.
Thank you, Reinis, for the very interesting talk. So we have a few questions from the chat.
Yes.
So the first question is from the Pile Sirogin. Pile.
Hello, do you hear me?
Yes, I do hear.
Okay, thank you very much for a very beautiful and fascinating presentation. So my question is related to the shape and envelope of power supply device and its spectrum. And it is well known that we can power any coil with clear sinusoidal or rectangle pulse. And if we look at the output stage of power device, we see that it can work with MOSFET and IGBT, and unfortunately, it has high order harmonics. So can you comment what type of power supply did you use, and did it contain high order harmonics, and maybe does the question impact of with a high order harmonic was studied? Thank you very much.
All right. We did use LDAC alternating power supply. It creates, we can switch between the two frequencies around 8.5 and 17 kilohertz. It really does the math and adjusts itself slightly the frequencies. And the power of the supply I used, the power was up to 20 kilowatts. We probably used maybe half of it, maybe up to 10 kilowatts in these levitation experiments and induction heating experiments. And I'm trying to understand your main question about higher order harmonics. It would be interesting to see the actual shape of a sinusoid, since these power supplies usually chop it up and reconstruct it. And I won't be able to answer this precisely. I can only speculate. I can attest that the phase shift in these experiments is really also important, since the induced current is in a different phase of the applied current in the inductor, and sometimes the phase shift creates these effects of rotation, which is important. But I'm not sure about the higher harmonics. Do they do anything worthwhile? So, yes.
Okay, thank you.
So the second question is from Oleg Burmistrov.
Hello, do you hear me?
Yes.
Okay, thank you for nice talk. I have a little question about electromagnetic subtlety. For example, the maximum load in the induction oven is 50 kilograms. Only 1 kilogram was charged into the oven. In this case, the dangerous level of electromagnetic fields can be generated about around the induction oven. Do you have research that?
I'm not sure I understood the question. You mentioned a case where we have fully charged an oven and only partially charged, but what kind of oven you mean? just maybe you can expand on that.
I mean, if you oven not fully charged, you have dangerous level electromagnetic fields around your oven.
All right. It's true that that the size of the conductor and it affects the total magnetic field, and if there's no load inside of it, it affects surroundings of it. The question: does it become dangerous to us? I don't immediately see it, since the field values are quite low. The magnetic field ones, it drastically drops. The stray magnetic field around the inductor drastically drops off with distance, and no physical effects can be felt if I, let's say, put my hand inside of it, even in an empty coil, since there's no microwave heating or that kind of effect. So I don't see any danger. It is true that the load changes when we don't have it or we have less of a material. It's also quite important in our, let's say, steering applications, where it's really difficult to steer half-empty container or to heat a really small object in the same inductor, simply because the induced electrical currents are too little. But in these cases, there is no danger when it's not loaded.
Okay, thanks.
And the third question from the pile below.
Yeah, thank you again for a really brilliant talk. Very nice one. What I was not really able to understand at the beginning, you have shown some semi-levitating setups and was claiming that you have AC and DC current there. Yeah, and after that, you was also mentioning that as soon as you have alternating current, you are also using DC magnet in order to prevent all these oscillations and so on. And at the end, you told that with DC magnets, yes, so this is another kind of levitation. Can you please clarify at this very beginning of the semi-levitation, what is the reason to use both AC and DC currents there? Because of course, DC currents will produce some permanent static magnetic field, and why this AC and DC are being used there?
All right, I'll go back to the relevant slide. I made maybe a little bit of confusion in my terminology. There's been slight confusion, so I'll try to explain it a bit better. These are the experiments. And this is the setup. It's true, this molten droplet is put in alternate magnetic field, which we call like AC field, and so on. And DC field was meant as here, if I wrote BDC, that's meant exists static magnetic field. It's created solely by a permanent magnet system. So essentially, there is one coil, one current, and in some cases, there is a magnetic field, static one, created by permanent magnets. And the reason for it, essentially, if I write out Lorentz force, maybe I had some formula somewhere here. So maybe up here. Okay, this is the Lorentz force. It's a cross product of induced current and magnetic field. In a case where we have put some kind of metal inside of the inductor. We have induced currents, and the magnetic field of the coil who created these induced currents. So we are working here only the multiplication is by multiplying induced currents and by looking at the magnetic field produced by this coil, which is the sum of induced magnetic field and applied. However, when we take external magnetic field by a permanent magnet, we can tremendously increase this magnetic field. That's essentially the reason why we want to use these permanent magnets in the setup here, since permanent magnet really increased the magnetic field in this fourth term, and we have stronger interactions. Yes. And then again, well, okay, I hope I answered some of it. You can ask more questions as well.
You answered it very, very great. I just wonder, so if I understand correctly, it means that like a main magnetic field in this particular system is DC field, but the current is induced by AC field.
Yes, there's no current injection. There's no terminals of current. The only current we have is induced current. And induced current will be AC. So the question is simple. So you have shown only this particular application of combination AC and DC, and after that you were showing always AC. Any particular reason why the people are not combining this for this levitation stuff? It's just simpler. Okay, maybe you will need smaller currents there if you use magnetic field in addition, like permanent magnetic field in addition to alternating one. All right. In these experiments, we did combine it to have a greater impact, to cause larger pressure oscillations, and the purpose of the project on these experiments was for material processing, to create a new material, and the levitation was not wasn't the aim. It was a side effect, let's say it that way, for semi-levitation. And the effects of externally applied magnetic field, they are multiple, since it in some in the direction, let's say if we applied one component of magnetic field, that component of movement or velocity will be dampened. That's called it's a dampening effect on what static magnetic field can achieve. So in levitation, you can maybe dampen the rotation or dampen the movement of it, but you cannot create forces, since this dampening term is dependent on velocity, if that makes any sense. So that would be like answer why we used it in our particularly semi-levitation experiments. We just wanted to have a greater impact using our electromagnetic technologies. In levitation, there is at first in this particular electromagnetic levitation or induced currents, there is little use of it. And another way how to try to explain it, these induced currents are harmonical in the workpiece, and the same goes for the magnetic field. So to get a static component, you have to multiply harmonic and harmonic part. If we have a static magnetic field and harmonic alternating current, and we multiply that, time average values will be 0. And so it doesn't create permanent forces. But this spinning effect and damping, it's in a bit different reference. That's why it can have force when there is velocity. It's here maybe writing out these effects separately would help to understand it and clarifying it. All right, that's the
Yeah,
best I can
thank you. It's
answer on
really
spot.
clear. Yeah, thank you. It's really clear. Thanks a lot.
Well, do you have any other questions? You raised your hand. No? Okay. So dear colleagues, do you have?
You said there was something in chat. I don't see the chat. You can check.
Just,
Oh.
Everything is okay now. So,
Oh, okay, okay, then it's good.
dear colleagues, do you have any other questions? So, if not, I'd like to thank speaker again. Thank you, Reinis.